Hello everyone, this is Monica Shaha and today I am going to teach you about the concept utilized in the searchability which is named as Routh-Hurwitz criteria. It is a very important topic and need to be learned, and so we move on to the next slide, which is the introduction, that why we wanted to study this particular method. First of all, this is a method which is formulated by A. Hurwitz and E. J. Routh, which provides stability information without the need to solve for the closed loop system poles. In addition, it requires only two simple steps, where the first step is to generate a data table called Routh array and then interpret that Routh array to tell how many closed loop poles are in the left half, right half, or on the j omega axis. By that method, we can find the number of poles, but we cannot find their actual coordinates. You can treat it as the disadvantage of this method, and then you might wonder that why to study this criteria when normal calculators or simple calculators are available to solve the higher degree of polynomials. It says that although we are interested with the characteristic equation, but if the denominator parameters are not known, then it is not possible for us to locate the exact location of the roots. But with the help of this method, which we'll show later, that it is possible for us to find out the cap or the zone where the system can be stable for that unknown denominator value. Let's move on to the next slide, which is the construction of the Routh array. For that, we require the characteristic polynomial, and let the characteristic polynomial be at the order of s to the power n. Now, the coefficient which is associated with this polynomial are a0, a1, a2 up to an. We will see in the next slide that how we are going to arrange these coefficients to construct the Routh array. And please do remember that as the highest power of s is n, we are going to construct an array which is having n number of rows. Now, for this Routh array, what we are going to do is that we label the rows with the powers of s from the highest power of the denominator up to the lowest power, which is s to the power 0. Next, start with the coefficient of the highest power of the s in the denominator and list horizontally in the first row every other coefficient. That is, if it was s to the power n, first was a0, then the coefficient was for s to the power n minus 2, then s to the power n minus 4, s to the power n minus 6, and so on. The second row list horizontally again, starting with the next highest power of s, and every coefficient that was skipped in the first row has to be written in the second row. So these two rows are constructed from the actual polynomial coefficients. Next, as we move on, then we have to calculate b1, b2, b3, which has to be calculated from these first two rows. And it shows that how I am going to calculate the b1. So let's have a look. b1 has to be calculated by a1 into a2 minus a3 into a0 divided by a1. Next, if I move on horizontally, we need to calculate the B2, and B2 can be calculated by A1 into A4 minus A5 into A0 divided by A1. Then we calculate B3, which is again calculated as A1 into A6 minus A7 into A0 divided by A1. Once this B1, B2 and B3 calculated, next we move on to calculate C1 and C2. How to calculate C1? Again it is B1 into A3 minus B2 into A1 divided by B1. Then we calculate C2, which is B1 into A5 minus B3 into A1 divided by B1. It continues up to we reach the lowest power of s, which is s to the power 0, and the coefficient of s to the power 0 has to be written. So this is called as Routh array, and our point of attraction lies in the first column of the Routh array. Before we predict the stability concept from this, let's have a look what the stability criteria from the Routh-Hurwitz says. It says that the necessary and the sufficient condition for stability is that the first column of Routh array should be positive. That is, all the elements will have the positive value if we wanted to have the system or make the system stable. If the condition is not met, then and if the sign changes exist, that time the clear instruction is the system is unstable, and we can count how many poles are located in the right side of the S-plane, and that is equal to the number of sign changes. Please note that plus to minus, if it is magnitudes are changed, is considered as one sign change. Again from minus, if we come across a plus value, then again it is considered as another sign change. There are different cases we come across when we wanted to solve the Routh-Hurwitz criteria, and for the time constraint, this time we are going to only discuss about the case 1. But let's have a look what are the different cases. Case 1 is the normal Routh array, that is non-zero elements in the first column of the Routh array. What about the case 2? It is a row of all zeros, and case 3, it is the first element of a row is 0, but some other elements are not 0. So when we are going to discuss the case 1, as such there is no difficulty while we form in the Routh array, but if there is any sign change, that time count the sign change, and the number of poles lying in the right hand side of S-plane is equal to the number of sign changes. So to explain or to understand this concept in a better way, we take a numerical example where the characteristic equation is given and S is having the highest power of 4, and it has been asked to comment on the location of the roots. So what we have done, so if it is the highest power of S, so from the s to the power 4 up to s to the power 0, we have tried to calculate the Routh array. So first is for s to the power 4 coefficient is 1, then skip this term, then the s to the square coefficient is 18, skip this term, then the coefficient is 5. Again we have this s cube where we have the coefficients which have been skipped earlier has written. Then we have constructed s square and s to the power 1 values, and as a result s to the power 0, the coefficient is 5, it is written. Then we have identified the first column and checked if there is any sign change exist in that. The answer was no. All the elements in the first column of the Routh array is positive. So what are the conclusion? The conclusion is there is no change in the sign change in the first column of Routh array. So obviously the system is stable, and as the polynomial is the highest power of s is 4, all the 4 roots are lying in the left half of the S-plane. So thank you very much for your time and patience. Have a good day.